continuity. Yeah, so start with continuity of a function. Definition is we're going to let x and y be topological spaces. Topological spaces. So a function f that takes x to y is continuous if and only if we have an open set V in the codomain, then the inverse image will be open. So the inverse image will be open in X.
Okay. This is actually the favorite topology question that gets asked on the math GRE.
Really?
Yeah. Mm-hmm.
The continuity question?
Yeah, the inverse image of the open set is.
Yep, and then you can also show closed. So closed sets get closed, but that's all equivalent anyway. But okay. They noted a few things that aren't necessarily definitions, but so if we take the inverse image of an open set in the codomain, we're basically taking the set of all of the elements in the domain space X, where if we map over, that's going to be an element inside of the open set. And so that means if I take the f of x and intersect it with the open set, then it's going to be empty if and only if the inverse image of the open set is empty. Okay. And then for bases, if y is given by some basis b, then to prove continuity of a function f, it suffices to show that if we've got the inverse image of the basis element, where B is a basis element, then we need this to be an open set. Okay. Let's see. So then if I have an open set V in Y, so V is open in Y, then that means I can describe V as some union of basis elements V sub alpha, which means that I can then have the inverse image of that open set as being the union of all of the inverse images of the basis elements, which gives that if I were to take the inverse image of a basis element, and that is open, that's going to mean that the inverse image of V will also be open. Because V's are open. So a unions of open set is open. Yeah. Coming from V. So we're requiring V to be open. Otherwise, this doesn't work. Okay. So reconstruct and turn to the epsilon delta, which is going to be specifically applying this definition of continuity to real valued functions fr to r, which will make the open sets just what we think of naturally when we think of an open interval. I didn't have time to do Because there's other kinds of functions, so you can take R to R2 or like R2 to R, R3 to R, things like that. So I'll probably go through and see if I can draw the picture, but it might be a little bit harder to draw on paper. But so if I take, if I want a real valued function f taking R to R, and I've got, well, that's not going to be big enough. Reals and reals. And the only thing we really need to get things started is we just need to choose, so given an x naught in the domain space, and we also need to choose a positive epsilon, but those are the only two things we need to get started. I can choose, well, I need a function first, so let's have a function coming through like this. And if I choose x naught to be in my domain space, here I'm going to have in the codomain space the element f of x naught. And then I've chosen a positive epsilon that I'm going to create an open set in my codomain. So if I choose that to be, say, something like this, then I can have f of x naught plus whatever positive epsilon I chose. And then down here, it's going to be f of x naught minus whatever epsilon I chose. F of x naught plus positive epsilon. And now this is going to, and when I look at the inverse image of V, so what I'll say is, okay, given this information, I'll say that V is this open set that's going to take f of x naught minus epsilon up to f of x naught plus epsilon. And because of that, then I take the inverse image of V. We just need to say that this is an open set. So here are some open set in the codomain. So I'll call this is the inverse image of V, which will be open in domain space. Because this is true, then by the way we chose x naught to be specifically in this interval, then x naught we know for certain is going to be one of the elements inside of the inverse image. And since this is going to be an open set, we said this is going to be continuous. This is open in R, and since this is open in R, and then the property in the basis, when we're talking about bases for topologies, is if I've got an element in an open set of a topology, then there's going to exist a basis element that's containing this element. So I know that the basis elements on the topology we use for R are the open intervals. So I can say then there is some open interval AB that's going to contain x naught that's a subset of the inverse image of V. So the thing is, it's an improper subset. So you could just take this as basis element that includes x naught, but it doesn't have to. So in this example, I'll show that it doesn't necessarily need to be exactly. So if you have a smaller basis element, so like if I maybe make A, right here, right? So if this is A instead of all the way, but we can have, so say that's B, and so we take just part of it, which is a subset, like I said, of the open set. And so then what we're doing is when we're really choosing the delta, that's why we need to take a minimum. So we're making that choice of I want delta to take the minimum between whether I go from x naught to A, so x naught minus A, and or if I go B to x naught, so B minus x naught. So then in that case, we would choose this one because it is smaller to be my delta. And if I do the same thing, apply it to both sides, I'm going to generate kind of another interval here, where this A I can write now as x naught minus delta, and then this, even though it's not necessarily B, I can still mark this as x naught plus delta, and we get a little open set inside here with delta. So the way it goes is we start by the hypothesis for this is that I need to choose some sort of point that's contained inside of the basis element that contains the point I'm interested in. So if I chose, say, like this value right here, x. So if I call this x, and if I assert that if the distance between my x value with the point is contained inside this interval delta, then what I'm really saying is if I interpret this as just inequality, kind of like how we did up here, then negative delta is going to be less than x minus x naught, which is less than delta. And then adding the x naughts is going to give x naught minus delta less than x is less than x naught plus delta. And then, oh yes, that's right. So x naught minus delta when we had it right here. This happens to coincide with A, but it doesn't have to because the x naught plus delta is less than the B. So we can, outside of this inequality, we can say that the A is going to be less than or equal to the x naught minus delta, which is less than x, which is less than x naught plus delta, which is less than or equal to B, which is going to be the largest for the basis element. But then what we really care about is just being able to say that A is less than x is less than B. Or essentially, if this is true, then x is an element of the basis element, which is a subset of the inverse image of the open set, which tells us that when I take the function value of this f of x into here, this is f of x, that it's going to be it'll also be contained in the open set B. So f of x is an element of the open set in the co-domain. I think he calls it the range space. So maybe I should start calling it that instead of the algebra thing, but which means, so to definably to be inside of V, it's going to be inside of the open interval here. So we can have the inequality that f of x naught minus epsilon is less than this element, because this element's contained inside of whatever that open interval is. So it'd be somewhere in between that and f x naught plus epsilon. And then when we subtract, we get, oops, 50 epsilon. Yeah, minus epsilon by itself, f of x with minus f of x naught, that's less than epsilon. And then by absolute value, we have that the difference between the function and the point will be less than. So that's why, so we get epsilon delta definition of continuity for x minus x naught less than delta gives f of x minus f of x naught less than epsilon, because of the open set V in the range space. The inverse image of that is open in the domain space.
Yeah, interesting approach that they're taking with the open set. Normally we do we imagine points. Right?
Like the sequence.
Yeah.
Yeah, limit points. Yeah, there was a way he did have a example with that, but I'm a fan of. Yeah.
Very good.
Nice. So yeah, there's epsilon delta. What's funny is thinking about the open sets was somehow more, I guess, mentally intuitive, then, because I remember you would teach epsilon delta in real analysis, but it didn't really click. I just had to memorize that
Mhm.
that was true, but not necessarily see why. So this was good. I think this addresses all of the general cases that was bothering me. So like why you have to choose minimum delta, and also why we're allowed to say that there is the interval that's containing here, and then why specifically we can take it up. So the relationship between the deltas and the epsilons is not really necessarily given, because if you don't talk about the inverse image of the open set, you won't know why the epsilon is going to govern. So I thought that I was trying to go deltas to epsilon
Mhm.
instead of epsilon, because this will always be, well, you can have subsets here, but this will technically, the inverse image will always be bigger than whatever your basis element you choose. So
And in fact, we're recovering this, and it's always been an artifact for the minimum delta. Really, that's always just been there to make it symmetric, so you can do absolute values. So you could actually just do it with sets, and you don't even need deltas really.
so instead of choosing,
You just leave it as an interval, as an open set.
oh, yeah, that's true. Because you kind of you just get to hear it at some point. So putting it in the basis element, yeah. But so this would be if you wanted to do the computation.
Right, to recover what you've seen already in Calc 1.
Cool. So now I'll just have to hold back whenever someone asks me what continuous function means. I'll be like, there are so many answers I could give to you right now. And it's weird because I'm tutoring a kid right now in like algebra 2. And so then they're doing continuous functions. I'm just like, just keep your pencil on the paper. That's all you need to know right
So I say that.
now. Okay. And then there's a pretty big theorem, which is just a bunch of equivalent ideas with continuity. So a theorem is we're going to let x and y be topological spaces, and then the function x is the domain space, y is the range space. Then the following are equivalent. Okay, so the first thing is that f is continuous. F is continuous. And so we're going to show that this implies that for all subsets of the domain space, that the image of the closure will be a subset of the closure of the image. And then we'll use that to show that for all of the closed subsets of the range space, then the inverse image of those closed sets are going to be also closed in X. Okay, closed in X. And then lastly, we'll actually go from 1 to 4 and 4 back to 1 for this one. But that for all elements in the domain space and for all neighborhoods, V of the basically what X gets mapped to in the range space, then there's going to exist a neighborhood U of X such that the image of U is a subset then of the open set and or the neighborhood of it. Okay. So let's see. I think I'll have space to put at least the proof of 1 to 2 here. So proof. And we'll take 1 and show that that yields 2. So we get to start with the hypothesis that f is continuous, and then we're going to have some subset of the domain space. And so the goal here is we want to show that if we have an element in the closure of the subset, then f of x is then contained in the closure of the image. So if we do that, then essentially we've given that the image of the closure is a subset of the closure of the image. So we choose V to be the neighborhood of the element f of x. And then the inverse image of V would then be open in X because neighborhoods are open sets. And then that says X must be in the inverse image. So then there's going to exist some point Y in the neighborhood such that the inverse image of the neighborhood in the does not intersect your subset. Wait, hold on, did I say that right? No, because it's not the empty set. So it does intersect, yeah. So there will be, okay, if I choose a neighborhood of f of x, then the inverse image of that neighborhood will be open, then x is going to be in that open set of x. So then I'm given a point. There will be a point inside of the neighborhood where it will actually intersect the subset A, because I've chosen x to be in the closure. Okay. And then if I intersect V with the image of the subset, I can just choose the Y to be the element, the point f of y, which gives that then f of x is contained in the closure of A, or closure of the image of A. And then I'll probably need to erase. Yeah, I'll just erase. Then we're going to do the second statement, the third.
Okay, so one thing, so just on the side here, draw a function that has a jump discontinuity.
Like a jump. So in
Yeah, so do a interval in the domain.
that contains the jump.
Yeah,
Okay.
and so then the range.
But this is an interval, so that's not open.
Right, but so the range will have to like yeah, right that. So the closure of the domain, because it's so I'm just thinking at the point where it jumps with the open circle, if we close that off, that's no longer in the range. So that's what, and the reason that's okay is because it's not continuous. Right, because the closure of the domain.
Well, yeah, because when you break continuity, then you're not going to be able to find the neighborhood that's necessarily going to contain the point Y. So that's why you can't break it. Because closing that's not going to address the gap in the interval. Because you still have to take a union, and then you're not guaranteed necessarily you could choose something in here.
Right.
Yeah.
Not gonna get.
So because that's not going to then come back down to here. So that won't necessarily, the inverse image won't necessarily intersect your point. Yeah.
Okay.
Now let's do that. Okay, so this one's giving that if we have the whole closure thing, then the closed sets. And if we have a closed subset of the range space, then it'll be closed in the domain space. So we'll start with B closed in Y, where A then is the inverse image of B. So then the way we've set this up, we're just trying to show that A is going to be closed. So we just want to show that A is closed. the first thing we see is if I take f of A, that is by set theory f of f inverse of B. And then we talked about this like I think on the very first day, where when you necessarily take if you put the image of the inverse image, then there'll be a subset of the subset in the there's a lot going on. Yeah. And then if I say that I have an element in the closure of this subset, then f of x, so we've shown this is this is hypothesis. So f of x is going to be in f of closure of A, which is a subset of the closure of the image. This is a subset of the closure of B. And the closure of B in this case is B because we have high hypothesis that B is closed.
Go.
So then that lets us say that if I want to choose an element in the inverse image of P, which is A, and then that element being in A is essentially saying that the closure of A is a subset of A. And so A is a closed set in the domain space X. So yeah, this is where all the fun goes down, is using the hypothesis for B. Okay, so that's 2 to 3. There's 2 more parts to this. We'll do 3 to 1 to complete that loop. And then we'll do 1 to 4 as an if and only if. Which is actually pretty reminiscent to the definition of continuity at a point. I think it's essentially equivalent if you were to change it into restricting it only to functions R to R. Yeah. Okay, so 3 to 1. That's going to be if I have V is open in Y, and then we're going to define B to be the complement of V with respect to Y. And the reason we're doing this is because this is the one where we're saying that if we have closure, so a closed set in the range space giving a closed set in the domain space, then it'll be continuous. Oh yeah, so this is like the other way you could have defined it technically, if you want to. So in this case, the inverse image of B is the inverse image of Y, and then the complement, so inverse image of the open set V. The inverse image of the range space is the code. Just the domain space. And then we still have the inverse image of an open set. Now, we see by definition, so if V is open, then the complement of that open will be closed inside of Y at least. So B is closed in Y. And because B is closed in Y, then the inverse image of B will be closed in X. So that's this hypothesis, which then gives that if F inverse B is closed in X, so in other words, F inverse B is closed, these are the same set. This is closed, and this is the complement in the domain space X. So whatever this set is has to be open. So by definition, the inverse image of V will also be open in X, which is what we wanted, right? We wanted to choose an open set in the range space and then have the inverse image be open in the domain space. So yeah. These kinds of theorems remind me of having to do like invertible matrix theorem, daisy chaining, all of the implications. I'll probably be able to fit the 1 to 4 and 4 to 1 on this. So one more. We'll start with continuity. So if I have a point in the domain space, and V is the neighborhood of whatever f of x is in Y, then I can have U be the inverse image of the neighborhood, be a neighborhood of X. Oops, wrong way. Such that the image of UX is a subset of the neighborhood. Let's see, is that right? So I choose an element, V is the neighborhood. So if I let this be in X now, then that will be a yeah, okay, that's a subset in V. And then that's pretty much all you got to do, because we're just going from continuous to let's see what we're trying to do. Oh yeah, no, yeah, the existence of a neighborhood, that's a subset. Okay, so that's it. That's pretty straightforward. And then going the other way is now I'm going to start with an open set in Y. And then of course I'm going to still want to end up by saying that then the inverse image of this is open in X. I can say that the element X is in the inverse image of whatever that's going to be. And so we have f of X. This element is going to be in the open set B. And so therefore, by hypothesis, there's going to exist some neighborhood we can call U of X, where the image of this neighborhood is a subset of the neighborhood B. So hypothesis starting with 4. And then this tells us that the neighborhood UX is a subset of the inverse image of B. And the inverse image of V then can be described as some union of the neighborhoods UX. So some union of the UX's. And we can do this because each UX is open in X. And so union of open sets is going to be an open set. So this will be open in X. All right. So there's continuity of effects. And I want to do homeomorphisms. Homeomorphisms, they nod back to group theory more, because you get the isomorphisms are specific bijective correspondences, and so it's going to be similar. So we can define let X and Y be topological spaces. Topological spaces where we have a map X, Y. This will be a bijective correspondence. So if F and its inverse defined by taking the range space into the domain space, if both of them are continuous, then we say that the map F is a homeomorphism.
So do we need both F and F inverse? Doesn't one imply the other? It's interesting that they would just put both.
Well, right, because then we can alternately define this to just say that a homeomorphism is a bijection f x y, where if the image of U is open, that will be if and only if U is. So it goes both ways. So that's why you don't have to talk about the inverse per se, because if I take a subset that's open in either domain or the range, if the image is going to be open, and then going both ways, if then I have an image being open, giving the original subsets open.
So open has to map to open both ways.
So I guess, well, because you weren't sure if we had to restate
Yeah,
essentially.
I am not sure.
So
Still not convinced, but okay. I'm just trying to find a counterexample where one way is true and the other one isn't.
oh, the way he handles that is he does embeddings. So it's where not necessarily, so if you take where the image of the domain, so if it's not completely bijective, so if you go into, and if you have an injection, then going in the inverse direction, you need to restrict y onto the image of, so basically image of x from f. If you can go that way, and then you still have continuity, then you would just call that an embedding of the topological property. But so maybe that's why he distinguished between them, but I'm not completely sure.
Yeah.
So a property of x that is entirely expressed in terms of the topology of x yields via the correspondence f a corresponding property for the space y space y, then such a property of x is a topological property of x. The English is probably, grammar's probably not great, but basically it's analogous to the idea where if you have an isomorphism between, they don't even need to be groups, so they can just have binary algebraic structures where the relationship between the way the binary operation is defined on the elements of that set is those are considered properties, so like associativity. Whereas now, instead of restricting it so that we're in the context of topological spaces, then the way that the topology has been defined are a property that results from the topological the topology on the set will be also mapped over through f. So a topology preserving map.
Right. So openness is a topological property.
Yeah.
But there are others as well.
Let's do the embeddings. The definition of embedding.
Maybe it will reveal itself.
Which is why I want to erase this one so we can compare them. Because now that you said it, I am kind of curious too, because
Just
if
trying
there's
to think of a counterexample just in R2, but
okay, so let f take x to y. So instead of being a bijection, we'll have this be injective and continuous map. And then we'll have, of course, x, y are topological spaces. And then if we so we'll define a set Z to be the image of X, just to make notation less confusing later, which will be considered a subspace of Y. Then the function f prime that takes X to the image of X from F. This is bijective. And then if f prime then is a homeomorphism, that is if I were to then go from the image back to, then that would be continuous as well. It's a homeomorphism of X with Z, then the map, that's F from X to Y. The injective map is a topological embedding. Or just embedding of this domain set or domain space X and Y. So this is taking care of, because there are certain functions, so it's like if you had a parabola, that's
Right.
R to R, where the codomain, so that's not necessarily bijective, it's injective, because you would have R going only to, so the image of R would then just be the closure of R, when the closure of R is a subset technically of R. And then if you want to go the other way, closure of R to R would need to be continuous in order for it to be an embedding.
So is embedding with an I or with an
They have it with an I, like embedding, to embed something.
Oh.
The
sort of like
way I kind of tried to see it was like as if you were trying to like stick something into, so it's like it's the same size as it, but you're putting in at least the same properties for a localized portion of the entire thing.
that?
But I don't know
Right.
how.
So yeah, it's an important thing. It's embedded inside of it.
So there's just some examples here to finish. Step down from the clouds for a second. I don't know if this is even the cloud. This is more like the ozone layer above the cloud.
I'm still having a hard time if it's one-to-one and onto,
Right.
and F is continuous.
Then F inverse will be continuous.
I would think so, but
Yeah.
I'm not sure why he specified both F and N.
Well, he is really tedious too. I'm pretty sure it'd be an equivalent definition because you could, well, what you could do is you could define without mentioning the inverse, make a really fast corollary and just say, well, we can easily show that but that's more of an algebra problem to have the mapping. So he's probably, because he's not assuming algebra per se all too much in this opening part. That's probably why. Because if he wouldn't have included that, he would have had to added the caveat that the other direction works.
Just didn't want to go there. Okay, I'll give you that.
So I think that's probably what it was. Just an editorial decision to save space in the section. Didn't want to have to explain something that he thought was too obvious for he might have made it an exercise. That would be unsurprising. Okay. So if I have a real valued function R to R, which is going to be defined by f of x into the line 3x plus 1, then its inverse is going to be from R to R, defined by f inverse y, given by 1/3. Let's see, what does that be? It would be like y minus 1. And then, so the conditions are met. So we have that f, I mean, we've proven lines to be bijective last 2 years ago. And so f is bijective. And also line, these are lines which are continuous. F and F inverse are continuous. So F is then a homeomorphism. A homeomorphism. And then you can extend that to, if I take a real valued function R to R defined by some y, f of x is equal to mx plus c, and not equal to 0, then you can always guarantee the existence of the inverse, which is just going to be continuous as well. And because the line is bijective, then you'll have all hormone. So linear equations are, generally speaking, homeomorphisms, so long as they're not flat in the range space. Okay. And then if I say now do specifically -1 to 1 as an open set in R to R, this is defined by f of x is x over minus x squared. So we make a domain restriction on R that we can say that this is a continuous function. And then its inverse, R to then -1, 1. Just swoop those around, which is defined by f inverse of y, which is the 2y, 1 plus the square root of 1 plus 4y squared. This is a bijective correspondence. So f is bijective. And then these functions are continuous specifically on these, on the restriction. So this only works if we take the open set -1, 1. So f and f inverse are continuous. And so then f is a homeomorphism. And actually now, because I was talking to a friend about, we were having an argument about whether or not the inverse function, so 1 over x, is continuous. And I think the issue comes down to how you choose to define function, because you can have it as that relation where you just specifically remove 0, or if you're making, so you could choose to interpret that as f, where you take the union of -infinity, 0, union 0, infinity, and then if you take that union to R. Or I think what happens though is most people kind of assume that every single real valued function is gonna go per se. So the mistake I think is that as if I understand it correctly, I think from algebra, technically 1 over x is not R to R. So this would actually be just nonsensical to then give 1 over x by that, because you couldn't say 1 over 0 at the point of discontinuity. But then at that point, is it just undefined or discontinuous? Infinitely discontinuous.
That's 0.
Or, well, this is probably accounting for the function with the discontinuity. And then if you wanted to remove the discontinuity, you would just make a domain restriction, probably. So I could probably say f R plus 2R, right? So then in this case, that would be continuous.
Yeah.
But if I tried to turn it around the other way, R to R plus. So then if you were to do the homeomorphism, you'd have to choose to do it on specifically. So then you could do it on the other side too, if you really want. Yeah. Okay, I think I'll have to look ahead on what the next section is. But there's going to be.
And then that won't actually be an embedding. You just restrict it to R plus because it only goes to R plus. Okay, that's cool.
Right, because this is technically what the original function is. So this is a subset of.
Yeah, and they actually do talk about that later, how you can do bits and pieces and like have an atlas.
I think they do cut and pasting later.
Oh, they do?
Yeah.
Okay, yeah, I remember that. Yeah.
I don't remember which section that is. I know it's later on. But yeah.
Cool. That's awesome.